Good morning, everybody. Thanks for being here. The project I will talk about today is about symbolic categorization and revolves around a very simple yet fundamental question. That is, how do we... Thank you. How do brain activity, human brain activity changes after we acquire new knowledge about the world? In particular, we focused on a very specific question, that is, on a specific phenomenon, that is, what changes when we use symbols to parse a multisensory, ambiguous perceptual space into categories of recognizable objects. We created an artificial stimulus set of 16 multisensory animated objects. You can see they had the same shape, but they varied in their size and in the pitch of an associated sound they produced during the little squeezing animation. We had 4 size levels and 4 pitch levels created for each subject. And the 16 objects were created by merging together the 4x4 levels of the 2 features. Then we divided perceptual space into 4 categories by applying 2 sensory boundaries, one for size and one for pitch, and we assigned to each category an abstract name. Now, for instance, object 1, which is the smallest one producing the lowest sound, is an exemplar of care. We trained 21 participants for 9 days in associating each object to the correct name using a delayed match to category task. And crucially, we recorded using fMRI brain activity during the presentation of both objects and words before and after learning. During the 2 fMRI sessions, participants performed different versions of a one-back task. During the first fMRI, they performed a one-back task on stimulus identity, meaning that they had to press a button anytime they detected an immediate repetition of the very same stimulus, either object or word. And during the second fMRI session, they performed a one-back task on category identity probed by object name association, meaning that they had to press a button anytime an object was followed or preceded by its categorical name. Also, during the second fMRI, they performed the same one-back task on stimulus identity they performed on the very first day. No, it doesn't work. As we were interested in isolating those brain regions that represented, after learning, the categorical knowledge participants acquired, we implemented a whole brain searchlight on the categorical task. Within each sphere, we applied a cross-modal correlation analysis that basically tells you whether the distributed pattern of activity evoked by objects, by the presentation of objects, was similar or not to the corresponding category name. And the results showed 2 areas, one in the left angular gyrus and one in the right hippocampus, as involved in this task. In particular, it was interesting to notice that only the left angular gyrus showed the same similarity pattern also in the post-learning stimulus identity task that didn't make explicit the object name association, and this didn't happen in the hippocampus. So this means that probably these 2 areas had different roles in the process of retrieval categorical information, and we further investigated it by asking whether these 2 areas were differently representing the input modality of the stimulus. We did that by implementing neural decoding procedure. A neural decoding procedure. Basically, we trained a support vector machine to distinguish between just object and names, no matter the category. And we found that no matter the session, so no matter post or pre-learning, the right hippocampus was not able to distinguish the input modality, while the left angular gyrus maintained this information about the basic metric details. We further investigated the representation of our stimuli in the left angular gyrus as it maintained more stable identities of our objects, and in particular we asked whether these object identities changed after learning, were affected by our learning. And we did that by implementing a split-half correlation analysis that tells you whether a brain region is differently representing objects. And we found, surprisingly, that the left angular gyrus was not representing these objects before learning, but it was doing that only after learning. And this was surprising because participants performed really, really well during both fMRI sessions. I didn't show you the results, but it was the performance was above 90%. And one possibility is that they didn't recognize a single object identity as the same object throughout the whole experimental session, but only on a one-back fashion. And to test this hypothesis, we implemented reproducibility analysis that tells you whether the variability of the evoked pattern for each trial of a given object are less variable, meaning that they are more stable, more reproducible across an experimental session. So we extracted a beta series for each object presentation during each trial, running a separate GLM, and we calculated the mean angular deviation and an index of such variability. And we found that across objects and across subjects, this variability actually was reduced, meaning that the representation was more stable. And this was further supported by the fact that a higher portion of voxels in the left angular gyrus distinguished our object identities after learning, as indicated by a simple F-test. Also, we extended the description of how object identities were differently represented in the brain to sensory regions. And in particular, we extracted those sensory regions that were positively activated by the visual and by the acoustic components of our multisensory objects by means of a separate functional localizer. And in these two regions, we calculated the similarity in evoked pattern of activity between objects that varied only along size and not along the pitch dimension, and on the other way around, only along pitch and not along the size. And we found that, for instance, in visual areas, objects that differed in their size were represented more differently after learning, and objects that differed more along their pitch were represented more similarly. And we found the opposite pattern in acoustic areas, meaning that these sensory regions showed increased sensitivity for the preferred dimension, decreased sensitivity for the non-preferred one, so an increased sensory segregation. Finally, we decided to put all these findings together, and we tried to describe the network dynamics, so how the information flowed during the categorical task, so only post-learning. And we actually missed one node in the network, that was the brain region responding to visually presented words. We isolated the region using univariate contrast, words over baseline, and of course we found well-known visual word form area in the left inferior temporal cortex. And we used dynamic causal modeling and Bayesian model selection to find a plausible neurobiological model that could explain the flow of information between these nodes. Now, we tested 4 models. I don't have time to illustrate all of them. All of them basically assumed sensory inputs coming from sensory dimension and differently described how the information flowed either from sensory regions to the left angular gyrus or from sensory regions to the hippocampus, and then how the information flowed from hippocampus to left angular gyrus or vice versa. The winning model was the one that I reported here, model 4. As you can see, the probability was pretty high. Basically, information arrived in the relevant sensory regions. It was integrated in the left angular gyrus, and the left angular gyrus communicated through feed-forward and feedback connectivity with the hippocampus. So to summarize, we had some evidence of the involvement of the left angular gyrus and the right hippocampus in the process of retrieval or constructing symbolic categorical spaces from perceptual spaces. And these effects affected also sensory regions, where we showed increased sensory segregation. And the role of left angular gyrus and the right hippocampus was probably different. And we suggested probably the right hippocampus here, in light of its invariance to the presentation modality, might act as an interface to recall the sort of conceptual or abstract identity of the category. And this is in line, for instance, with intracranial recordings in human hippocampus. And that's it. I'd like to thank my supervisor and Valentina, which is a postdoc, and all the other people I've talked to. Thank you very much.
Very